Hello, my name is Lily Alterman, and I'll be presenting to you Lab 2, which is about motion of a falling object. So the purpose of this lab is to observe the motion of an object that's falling, and then from this we're going to create an analytical model using the data gained from the computational model and the physical experimental data, and then we're going to compare these computational models with drag measured and without drag measured, and then we'll be discussing the outcome of that. So as a little introduction, Newton's second law, which is also known as the momentum principle, relates the total interactions to the changes of the motion in the system. And then with this lab specifically, we're going to be working with the force of drag. Drag is the direction directly opposes an object's direction of motion, and the magnitude is proportional to the square of the object's speed, which is also known as turbulent drag. And this can be represented by this formula right here, the force drag equals the b variable, and then the velocity squared and the velocity b hat right there. And then our Newton's second law also gives us the following velocity and position update formulas, which we will be using to create our computational models today. And terminal velocity is when the drag equals the force of gravity, and thus the whole net force of the system is zero and there is no acceleration. So now we're going to be using Tracker and WebPython for our experiment today, and we will have two separate simulations in WebPython. And right here, this is the objects that our motion will be studied. So our initial conditions, which are the same for all models, are that we can assume that the object is only moving in the y direction, the object started with zero velocity, and the floor is flat, to my understanding. And for our system, the object in motion will be our little crocheted strawberry. The mass of the object was measured to be 4.48 grams. Around the system, there was a meter stick, but otherwise no other physical conditions interfering with this falling motion. And the only forces acting on the object were gravity and drag, and as said before in one of these computational models, drag will be ignored. So now we have our tracker simulation. As you can see, I dropped a little strawberry and tracked its motion and got its position to be able to do the following calculations for our computational data. So our WebPython code, as you can see, I put in the ball's mass right here, and we did set the position and velocity vectors to 0, which we did assume with our data, and then we did change the delta t to 0.033, which is directly related to the frames per second in my video. And then we have our j hat vector right here, the force of gravity. The most important thing right here, since it's the gravity only model, b was 0, and we did set our time then to 0.5 in correlation with the video. The force of gravity then was set equal to this formula right here, which was basically derived by using Newton's second law and the Newton's law of motion and the y direction. And then we used Newton's update formulas to get that right here, and this is just advancing the clock by the delta hat variable. Now, when we did our experiment, the only difference between the gravity code and the code with drag is these two parts right here. I did calculate for our b value, which we got right here, and since we are accounting for drag, this was not 0. And basically, our F net now equals the force of gravity plus the force of drag, and our force of drag was calculated using the ball speed and our b variable and the j hat right here. Now the comparison of our computational models. In the result of that code, we have here our model with drag. As you can see, we are approaching a terminal velocity right here, approaching a straight line. Meanwhile, without drag, it's a constant velocity over time, and there is no sign of approaching a terminal velocity right here. And which brings to our main difference in these. When we had drag in it, we are able to start to see an approach of terminal velocity, unlike when we have without drag, we do not see any of the approach there. And now the what if and what does questions. Basically, what does it mean? The computational model, including drag, is going to be the only one that's going to predict a terminal velocity as shown before on the previous page. the other one has a constant velocity, and thus we cannot really predict where terminal velocity would be. And if a object was thrown downwards, the terminal velocity would remain the same since the variables that is calculated by are not impacted by being thrown downwards. Thank you so much for listening today, and I hope you have a lovely day.